Okay, guys. Hello, everybody, and welcome from my side. I want to talk about the evaluation of vehicle fleet electrification. And my name is Sebastian, and I come from University of Erlangen. First, the agenda of my talk. I want to begin with a brief motivation why the simulation of electrification is needed and important. And then I want to present you our simulation framework, which is actually WAINS, and our additional modules, which is the electrical vehicle model, the infrastructure model, our scenario controlling model, and at the end I show you some hopefully interesting simulation results and an outlook to our future work. Okay, I guess every one of you have heard about the climate change. We have to do something to decrease CO2 emissions, and one step towards less CO2 emissions is the electrification of traffic. Unfortunately, we can't just replace all our combustion engines with electric cars from one day to another. So one step for a first field trial is to replace vehicle fleets from companies. Companies usually have hundreds of cars, and they have different ranges, different jobs, and we work together with one company who is really interested in replacing their vehicle fleet. But before they buy electric cars, they want to have answers to some questions like how many vehicles are exchangeable? Can we replace the whole fleet or just 10% of our fleet? How much CO2 reduction can we achieve? Is it worth to consider buying electric cars? And is there any cost reduction, which is actually very important for the companies? To answer these questions, we need simulations, and we developed a framework to do such simulations, which is presented in the next slides. Well, the basis for our simulation framework is the hopefully well-known WAINS framework. WAINS coupled the network simulator OMNeT with the traffic simulator SUMO. In our case, we imported the map of the whole city of Nuremberg. Okay, my pointer worthless. Okay, from OpenStreetMap. So this gives us the opportunity to use realistic maps for our simulation. Why Nuremberg? Because this is the city where the headquarters of our cooperation partner is placed. In OMNeT, we do all the modeling stuff. So in OMNeT, we have a model for our engine, for our battery, for range extender, charging stations, recuperation modules, and so on and so forth. And in the next couple of slides, I want to show you some of our modules. First of all, we need a model for the electric car. Unfortunately, until now, we only have combustion engine cars modeled in OMNeT. So what we have done and what will be presented at the IVC in 2 weeks is a model for electric car, which is based on the kinematic of the electric car. I don't want to hurt you with equations, just that you have a little insight. The SOC of the battery, so the state of charge, the level of the battery is calculated based on the observed power flows during a time slot. So we have power that goes into the battery, like the power from a range extender, and power that flows out, for instance, that is needed for the engine. And in the paper we showed that we can model, or we can calculate all the power flows based on only one input, that is the speed of the car. Luckily, the speed is what SUMO gives OMNeT as an input. So we have a very lightweight model here with only one input, and we even validated this model with real data, and it fits quite good. Besides the model for the car, we of course need a model for the infrastructure. In our case, we need charging stations because unfortunately cars, or the range of current electric cars is not that much, so we can drive 50 or 100 kilometers. So we need to recharge our cars, and therefore we need charging stations. Our charging stations are modeled in the following way. We can place as much charging stations as we want on the SUMO map, and we can set different power transmission rates. We work with with the two typical and standardized transmission plugs. This is the type 2 maybe in English, plug with 11, 22 and 44 kilowatt, and the usual German Schuko plugs with up to 3 kilowatts. Of course, we can adjust the capacity per slot for our charging stations. So every charging station has only, I don't know, 4 plugs. And for all the cars coming after the first 4, we have a first come, first served queue. For all of you guys who haven't seen Sumo yet, here a little video. Here you see a electric vehicle, some background traffic in yellow, and a charging station. The car charges at the charging station until the battery is full or full enough, and then proceeds with its ride. Okay, so we have cars, we have charging stations, but of course we need a nice scenario. For controlling the scenario, we created a scheduler which creates jobs that can be taken by the cars. We can create jobs, I don't know, every 10 minutes if we want, but we based our job scheduler on real data from our cooperating partner. There are different strategies for vehicles to take jobs. We can either take jobs greedy, first vehicle who wants to have a job takes the job, or we can assign the job to the vehicle with the highest SOC. The distance the car has to drive can also be the same distance for every job, like 10 kilometers, but we also based our distance on a distribution that comes from our partner. And yeah, it is done in a way that we choose a random point on the map that is some kilometers away and let our car drive to this destination and back. And we can set the background traffic. Okay, simulation results. As you have seen, we have many parameters we can set. We can use different battery capacities. The more capacity we have, the longer we can ride. We can choose different distances. We can choose different maps, either city or outside the city. We can have different schedules and so on and so forth. And out of the simulations, we can get various data. Trains, so energy the cars consume during the ride, different speed profiles in the city, outside the city, the amount of charge power, which is important for the companies because they have to buy the power, waiting times at the charging station or the waiting time for a job until it is processed, and so on and so forth. In the next 2 slides, I want to show you some, I guess, interesting results from our simulations. This is the unused vehicles in a vehicle fleet for our partner. In blue, the unused total vehicles. In red, the unused electro, and in green, the unused gas vehicles. As you can see, around 45% degree of electrification. Our partner buys electric cars which are never used during 1 year. So it is unnecessary to buy electric cars after 45%. And this is important for the decision how much electric cars our partner wants to buy. And in the second results, you see how much the company saves. So electric energy is cheaper than gas, usually, or diesel. And here you can see if we use a range extender, we can even have more savings in comparison to an electric car without a range extender, because we can drive more distances with our electric cars. But you see, there is a point where more electric cars do not bring more savings for the company. So if we use a car with a range extender, or our reference car with a range extender, we have savings from around, I don't know, 28%, but after 40% degree of electrification, there is no further savings. Okay, the outlook for our project: we want to introduce in our system intervehicular communication and also vehicular to infrastructure communication. And we want to show that we can have a positive impact of communication on the power consumption, e.g. to green light, optimized speed advisory systems, and that we can recover more power due to an intelligent and optimized recuperation level setting. That if we know that we have to brake, that the recuperation level is set to the highest level and that we can recover most of maximum energy, and that we can achieve intelligent load balancing at the charging station if the charging station communicates with the cars, if free slots are known to the cars. Okay, that's all from my side, and I guess it's time for questions and also discussions on weights and automotive stuff. Yes?
I have a basic question that also goes in the last slide here on it as a science. You said like the basic energy model depends on the charge of the battery and the motor output, basically the speed that you get from Sumo.
Mm-hmm.
I know from at our university we have a couple of electric cars, and when I talk with the drivers, they usually say like works fine in summer, but in winter we always have the problem. Well, it's cold, so you turn on the heating, turn on the light, and the range of the car goes from 100 kilometers to 50 kilometers.
Okay.
So, what about those external influences in general here in this relation? They don't play any role. Do you think it's quite necessary? Well, I think they are quite necessary.
It is necessary.
Do you have any idea how to incorporate them?
We have a power flow for consumers like window heat or AC. But until now, this is a constant value for us. So we can, of course, increase this value in the winter if we know that in the winter we consume more energy for other.
Would this be something to incorporate into Wayne's framework in general, like external events, external environmental characteristics, or something more like for Sumo? I don't know.
Well, the problem is we can, of course, put so much knowledge into this electric car model, we can really blast it up. But then we need more inputs, we need more calculations. And actually, we have done some, this will be presented at VTC in 2 weeks. We have done some reference rides, and in the first subplot you see the speed profile. This was a city ride. You can see around 50 kilometers per hour at maximum speed, and some periods where you stand still at some traffic light. And as you can see, the power flows from our model fit pretty good to the real power measured in the car. So our model works actually. But of course this was some ride at some time in the year. Maybe in the winter there's...
It's more like a general question.
Okay.
Environmental monitoring, especially for things like car networks, which might depend on such things.
Where to integrate this environmental modeling? I mean, I think this is a conceptual question from the software perspective. If you want to integrate these environmental parameters, in which part of the tool chain you would do this? You would integrate it in the Waynes, in the Sumo, or...
I guess in OMNeT.
Waynes.
I guess in OMNeT. Waynes is...
I mean, definitely not in Sumo as far as I understand,
yes.
Because it's only modeling the traffic flow.
Sumo is just traffic.
Yeah, okay, but we have similar problems in sensor networks when we come to think about like, okay, external interfaces, we want to measure temperature, anything. So is there a real environmental model for OMNeT, something like this? I think it might be interesting for you.
Yes.
If there will be something, but I think that's a general conceptual question for the last session. It's good to see how it works.
Okay.
So it's, two questions. I think it's interesting, this idea, how do you represent an environment, because environmental thing in OMNeT, because nodes tend to have point position rather than extents. But I was also curious, does your battery model incorporate the temperature of the battery? Because batteries are quite complex.
Until now, we don't have temperature of the battery considered in our model.
So,
But as you can see, it works.
is it really a strictly linear battery model that you're currently implementing?
Yes, it's linear.
It doesn't represent the aging of the battery on the multiple
Well, we are doing micro simulation here, so over a day there is no aging. Okay.
I mean, I have a specific question to your simulation. I mean, why is gain by electrification saturated with 50% of electrification? I mean, I'm a little bit surprised it's so early saturated.
Well,
is there any intuition behind that?
those are long-term effects, so this is more a macro simulation output. And, well, in our cooperation partner, the distances they have to ride are sometimes higher than the range of our electric cars. So if we add more electric cars to our fleet, they are useless because they can't take over more jobs at a defined point. So this, of course, depends on the schedule and the distances coming from the company.
But I mean, is this simulation modeling also recharging
Of course.
the cars? Yeah. So,
Of course.
Okay. So I mean, the distance. I mean, is a problem in time as you have to wait for the recharging.
Okay. Until now, we only recharge at the headquarters of the company.
Okay.
Yeah.
So so the charging station that we saw in the Sumo simulation are not considered actually.
It is considered, but only in the headquarter.
Okay.
Or in the headquarters. There are more than one headquarter.
But, I mean, there's no implementation reason for this? I mean, it should not be...
It was, the company wanted to have it this way. But of course we can put more charging stations.
Yeah, but then it should be a
It
bit different.
It could be better, yes.
Maybe I can add something to that. Our cooperating partner just happens to be an energy supplier provider, so they only want to charge at their own charging stations because electricity is a lot cheaper for them if they charge their cars at their own network. So that's why they only charge at that. And if we have jobs that are far away, like a job where a car has to drive 200 kilometers, we have to take a normal combustion engine vehicle. This distance cannot be covered in our simulation by electric vehicles, so we have this saturation of about, in this case, 30% of the equation.
Yes?
When you're simulating the background traffic, is it based on RTTI systems or floating car data from Google or anything, or just...
It's just random traffic. The cars are put somewhere and drive to some destination. Okay.
It would be interesting when you're driving in Nuremberg at 7 p.m. and you get in a traffic jam. Maybe you need more energy for heating or...
Yeah. If you have some consumers like air conditioner, you definitely need more energy. Otherwise, I guess it should be the same energy. Okay. Yes?
For the long-term goal, what will you do? I mean, this was now a project for a specific company, but I think there are many applications for the tool chain that you use and for exactly this model here. For example, companies, public transport companies, change to electric buses, something like this. They probably want to have similar observations, similar simulations done for them. Any long-term goal that you plan for this?
Well, we can exchange all the parameters to other electric cars and to other companies, other schedules. This is, of course, you can do that.
So it's going to be some open source chain, open source model that you're going to have, or is it just developed for this company and publish some papers and afterwards it goes to the company and nobody ever sees it again?
Well, we do make the model public. We're publishing the paper with everything I can explain. So I'm not sure about our legal obligations if we can publish the source code. If we can, we will do. But we have to obviously ask the parties they provide the money. But model is not that, it's a lightweight model and we publish everything about it. So it should be doable to just
Christoph?
What about your scenarios? I keep going on about publishing scenario data, right? It's not so much about having the right model, implementing it right. I think your simulation pretty much hinges on just simulating the scenario. Just like we heard, getting traffic in Nuremberg, or getting the heating right, or getting environmental conditions right. So is there actually a way to reproduce the results if I implement the model without knowing your scenario data?
Okay, we can of course use some generated distributions. So not the distribution that was taken from our partners, but some distribution. And then you can of course reproduce the output.
It would be very interesting to see how close I can get to your results when just taking a random distribution, right? Because it felt like yours had some very nice artifacts in it with this peak at some distance from the headquarters and this.
Of course, this is kind of sensitive data, you know. This
Yeah.
is like the corporation drawing a schedule. I don't think they want that.
I think that's pretty much a basic problem with every research we do. There's always extremely sensitive data in there. And we're doing some research for some cellular operators, and of course they don't want people to know which of their base stations just don't work. Or, yeah, like for the electrification company, they don't want to know when and how often they are driving and how long they are really taking to fix stuff.
Yeah.
So what can you do? I mean,
What we want to do is we want to provide the basis to just exchange the schedule. I mean, you can take any schedule, like buses, for example. It doesn't have to be the schedule of this specific corporation. But if you have the models that allows us to exchange the input and give out new results, that would be lovely, I guess. Would be enough. I don't think you want to reproduce that because you're not interested in this particular corporation. But if you have the simulation framework running, that should be desirable, I guess.
Just saying, I think at the moment there is exactly 0 reference scenarios for actually using the network simulations.
That's true.
For the mobile ad hoc networks domain, they had random waypoint, and that was good enough for some years. For vehicle networks, turns out that random waypoint doesn't work too well. But it seems like we're currently stuck with just having no scenario. I mean, just looking at the literature, everyone just comes up with their own scenario and says, okay, so now we prove our protocol works best in the west of Nuremberg, say 2 to 8 a.m. So, I mean, I'm kind of lost. Is there any way of coming up with a scenario and saying, okay, this is something that maybe your protocol should be tested against?
Well, I guess there's a problem in having a standard. I don't know. I mean, the distance is. It depends on the company. Actually, I mean, a bus company has always the same way, for instance, but for our company, they have millions of users, and it's difficult.
But for me, it comes down pretty much to trust in your results, right? If you present a paper, if you were to present a paper on that and say, okay, we got some nice results saying electrification kind of levels out after 40% degree of electrification, then how can I know that you actually implemented all of that stuff correctly? Because your model is hugely complex. Even if you said it was simple, took you a year or so. No, probably didn't take you. It looks complicated to me. It has math in it. So maybe you made a mistake, and I want to reproduce that and just say, okay, here's my proof. I implemented everything, and well, obviously you didn't make a mistake, and everything is brilliant.
Okay, well, the battery model is validated. So we had a reference car, we took the parameters of the reference car, and we got the same results. So I guess this is kind of a proof for the battery model. But of course, for those macroscopic effects, it's hard to really evaluate the output. But we are working on that.
Okay, so everything's still top secret. Okay, I I stop with the me questions.
Okay. Further questions?